Okay, just to briefly state the problem we're trying to solve. We will continue from this point on. We're trying to solve the problem of locating P identical facilities on a general network. The point set X stands for the locations of the facilities, and you want every vertex Vi to have at least one facility in the set X whose distance to Vi is within R over Wi. Wi are the given weights, and R is a parameter to be minimized. Capital D stands for the closest distance between Vi and the point set X. Now, we mentioned that instead of solving that directly, let's go ahead and fix R to an appropriate value and impose the same constraints, except that rather than restricting the number of variables here, number of facilities here, let's leave that free and try to locate as few facilities on the network as possible to satisfy the constraints. And that's going to give me whatever number of facilities. That number will be the minimum value we obtain here relative to a fixed value of the radius R. Okay? And we arrived at the conclusion that we are looking for a particular value R star for which the covering problem with that value gives you a solution with at most P facilities. And when you reduce the radius a little bit further by some epsilon, positive epsilon amount, the minimizing solution turns out to output more than P facilities. Okay? So that's the precise value we're looking for. And in doing so, I think the last thing I mentioned is the following. If you can restrict the search for R to some interval A, B, where A and B are, well, a natural lower bound here is 0, but you could also get better lower bounds if you wish. A natural upper bound B is you just pick some P facilities, not necessarily optimal, and compute the maximum weighted distance relative to those facilities, and whatever that maximum weighted distance will be, that will be a feasible value for this problem, which will certainly, when you fix it to that number, it will certainly give you at least, it will certainly give you P facilities that would satisfy the constraints, okay? Because you've actually picked the facilities to satisfy. All right, so you can search for R in this interval using, say, bisection search. So you begin with somewhere in the middle or the midpoint, and then once you solve, you either get QR less than or equal to P, or you get QR greater than P. If you get QR less than or equal to P, that means R is sufficiently large, so you might want to reduce it. In which case, of course, whenever this is the situation, you truncate. What do we want to do? We want to reduce, so you truncate or you keep AR and you truncate the remaining part from further consideration, because you can reduce R down towards the lower bound. Okay? In the second case, this is at the beginning. Of course, as you keep doing this, the lower bound may become something else, whatever it is. It just keeps shrinking. So in this remaining case, of course, The lower portion is deleted from further consideration. The upper portion is retained. So you repeat this using the most recent interval you've got. You assign the role of A to R in the second case. You assign the role of B to R in the first case. And then using the same, or using the new interval, you just repeat the process. Each time you split the interval, get rid of 1/2 of it, and this will, of course, get you to a rather small interval in, say, k steps. At that time, what's the length of the interval you would get in k repetitions? 1 over? Yeah. You would get, if you repeat this, say, k times, each time you're halving the interval. So your final solution you would get would be within your final solution would be within 1 over 2 to k units of the optimal or the actual value you're looking for. Okay? Does that make sense? Okay. Times B minus A. I don't know. Is that true? Yeah, it depends on the length. Yes, you're right. I forgot these things because it's been a long time since I really thought about that. Okay. All right, so, but I told you that actually we can do an exact search and find the exact value. Okay? So finding the exact value of R star, which certainly supplies you with the value of RP, is possible. Let us define, relative to a pair of vertices I and j, the number bij by the distance vi x let's multiply this with the vertex weight. Wid vix, which is the same as wj vjx, distance vjx, where x is the intersection point defined by this pair. Let's make it x sub ij, just to emphasize that that's a particular point on whatever edge. Actually, that also depends on the edge under consideration. So, in fact, I don't want to give you too much notation, but you might want to also restrict it to a particular edge under consideration as long as it exists. If it doesn't exist, so of course you don't define that one. So where x is the, so let's call that bij value relative to edge E. xije is the pairwise intersection point for vertex pair I and j. Now, that notation unnecessarily complicates the situation. All you have to do is you just compute this for each edge and for each pair of vertices, and those numbers will certainly supply you with possible values of RP. But there's an easier way to envision this. So better yet, let V prime be the point set consisting of vertices with union P. P is the set of intersection points. I think that's the notation I used before. And let Bij equal Wi times distance between vertex I and, say, point, what did I call them? Let me just, okay, let's just call it, say, point P sub Pj, Qj, well, let's make it Xj, okay? So, let's make it Yj. I'm running out of notation here because I've used all of these symbols for something else. Okay, if you let Yj be the jth element of V prime, then, since you have finitely many such points, you can always compute by pre-processing the vertex to point distances, and you would obtain all these numbers Bij. Okay? Order the numbers Bij to get an ordered list consisting of, say, beta 1, beta 2, so on and so forth, up to beta Q. Okay? With the smallest element being the first one, the largest element being the last one, and the order being preserved in this way. Okay? We're just picking the distinct numbers. So this is not a list, this is a set that has all possible values for RP. Does everybody agree with this? RP is a number that will be supplied from those list of numbers. To me, that's very obvious, but in case you have any doubts, all we are saying is the following. We proved that V prime supplies at least one optimal solution. Okay? Which means that whatever points you choose from V prime in the optimal solution, in such an optimal solution, you will be looking at Wi times the closest distance from Vi to that vertex, that point set. And that point set will give such a Yj from among its elements. Okay? And that number will be one of these numbers, whatever it is. I don't care. But so if I compute all these numbers a priori and put them in a list, then obviously my best solution value will come from that list. Okay?
But since we are minimizing the maximum distance, the ith vertex should not be the one that is having the maximum distance value. So maybe...
Not necessarily. No, no. I don't mean that. So I'm just computing this for all I coming from 1 to n, and for all j coming from 1 to q. J refers to the jth point in V prime in the candidate list. I refers to the ith demand point.
I calculate all these values and then order them. Because
Yes.
this set is just for a vertex I. This piece.
Okay, yeah. The notation is a little bit misleading. But all I'm saying is, yes, you compute the BIJs for all possible pairs of demands and candidate points, and then order them. However many you get, you just have a new list with distinct numbers in it. Okay? All right. So clearly, RP is one of these numbers. Hence, we can solve the covering problem. Did I give a name to this before? I must have. Did I call it CPR or something? Did I do that? No? Well, if we didn't do that, let me just continue. Hence, we can solve the covering problem with parameters or fixed parameters R as many times as necessary by doing a binary search over the ordered list beta 1 up to beta q. So instead of working with an interval, you're working with a finitely many numbers. They are ordered. And when they are ordered, of course, whenever you begin with some element close to the middle. You solve the covering problem. You either truncate the lower portion or the upper portion, depending on what happens with the covering problem. So when you throw away 1/2 or some numbers from the interval will reduce in length, will reduce in number of elements by at least almost half. Okay, it doesn't have to be exactly half, but almost half. So this will quickly converge to the actual value you're looking for. Okay? What's the largest number of steps you would get if you have q elements in it? Huh? Log 2. Log q. Log q. Log to the base of q. Repetitions. This is the number of repetitions you would require. Q is at most how many? How much is Q at most? Well, V has n elements. P has n squared times e elements, which is certainly less than or equal to n to the 4th. okay, because the number of elements in the edge set could be as much as n to the n squared. So this is less than or equal to n to the fourth. Now, if you add n to it, it doesn't really change the order. And you're going to multiply this with n. So we're talking about n to the 5. A pairing of each demand with each member of this. Okay, so that's why we're multiplying it with n again. N to the 5 numbers in the ordered list, which means we're talking about log 2 to n to the 5th, which gives you that much, okay? Which is pretty, well, it's a low order polynomial number of repetitions, but each repetition will ask you to solve a covering problem, which we haven't talked about yet. So it depends on the complexity of how to deal with the covering problem. Unfortunately, the covering problem is an integer programming problem. It's called a set covering problem, and it's NP hard. Nevertheless, it's a solvable problem, at least for reasonable sizes. So we're going to go into that. So I'm taking this problem, and I'm going to formulate an integer program to solve it. The first thing is, of course, I'm able to restrict my search for x to v prime rather than to n. Okay? So with that, I have finitely many points. And I can define a set covering problem as follows. Let's define a 0, 1 variable xi for the jth point in the candidate list. So let xj be either 1 or 0. 1 if we open a facility or center or covering point at yj, the jth point in v prime, and 0 if we don't otherwise. Okay? So all I want to do is I want to minimize the number of facilities I open. This will go from j equals 1 up to q, where q is the number of elements in v prime. Subject to. Now the subject to part is not really difficult. All you have to do is to define a constraint of the following sort: aij times xj, j going from 1 to q again, greater or equal 1, with this is going to be written for each demand point 1 up to n, with xj being restricted to 0 or 1. Now, of course, I didn't tell you what aij would be. I'm going to in a minute, okay? But let's look at this constraint first. These aij's are coefficients to be determined by yourself. They are either zeros or ones. So whenever this aij is a 0, it doesn't do anything. But whenever this is 1, it picks up that xj. So you want this summation to be picking up at least one xj for which the coefficient is 1. Okay, that's what you're trying to do in set covering. Now, what is aij? aij is simple. It's a parameter to be determined a priori. It will be 1 or 0. It will be 1 if the weighted distance of vertex I to the jth candidate, yj, is less or equal r. R is a fixed number here. Remember that. 0 otherwise. So whenever yj is within an appropriate distance of vi, appropriate being within r, units of weighted distance, then of course aij is 1, so that whenever you declare xj to be 1 in that case, that that facility at that point will cover vertex I as well as possibly others, okay? Because this is written for each one. Does that make sense? I guess that's pretty straightforward. Okay, so that's your set covering problem. Sure.
Like a single model, like define xjr, like variables, and aijr. Then we also have to define like something like yr, and if it is 1, we let the other xj's.
That's interesting. So instead of solving this sequentially for different values of r, you want to throw all possible A matrices as dependent on R into the same problem. That's what you want to do. I don't know. Nobody proposed that except you. So now if you do that, there may be some problems. I don't know because I've never really confronted the situation before. But let's think about it. In that case, you might have difficulty unless you maybe, if you permit yourself to impose additional constraints to take care of any, weaknesses you might have in the problem. In that case, you would lose the set covering structure. That's a problem. And if you just stick to the set covering structure, then probably you will run into the problem of, some vertex being covered by a facility relative to some r, whereas something else being covered relative to some other r, and that's a confusing issue. It probably requires some additional constraints, which you may or may not want to do. Okay? Now, this approach is initially proposed by Minieka in a 2-page paper, technical note. Well, actually, it wasn't called technical note. Was it or was it not? Was it? Okay. Now, Minieka is a very sharp guy. He actually looked at the unweighted case, so WIs are 1, but it doesn't really matter. It does the same thing. He first observed the finite dominating set property that we just talked about. And then he said, rather than searching for R over the ordered list, he did the following. He picked a particular A matrix as defined by some choice of P points in the restricted set. So once you have your P points in the restricted set, that's a feasible solution for the P-center problem. And the maximum weighted distance relative to that would give you a particular R value. Okay? Now, for that particular R value, you are able to compute this matrix. Once you compute that, suppose you solve the problem, what do you expect? In other words, how many do you expect in the minimum solution? Greater or less than or equal? Well, if the initial R you pick, so let's call this R0, well, whatever, let's just call it R. This will be the maximum weighted distance relative to some arbitrary choice of P points. So, once you choose P points from V prime and compute the maximum weighted distance, it gives you a particular R. Then this R allows you to compute the A matrix relative to that R as defined by those numbers. Let me just emphasize the dependence by writing it this way. Now, when you solve this problem using that particular matrix, since X is already a solution, then by declaring whatever points inside X are, you just declare those xj's to be 1 and the remaining ones are 0. That would give you a feasible solution here, which would cover everybody. And you would obtain P. So that would be a feasible solution. So normally when you optimize, you get something either P or less. Okay? So, assuming that you've got exactly P, what would you conclude? If you get exactly P, you already have a P-centered solution that you supplied, and you're not able to do anything better than that, then obviously you are at the optimizing solution for the P-center. Do you agree with that? You agree. Okay. If you get strictly less than P, that means the initial R you've chosen is probably too large. Well, omit the word probably. It's too large. It's definitely too large. Okay? Sorry, too large or too small? Too large, too large. So, now what Minieka proposes is he actually, in that case, he simply erases certain aij's that used to be 1. He makes them 0. Which ones do you think? And then he will resolve the problem. Think of the unweighted case. Maybe that's easier. I repeat the question. He says, if you get strictly less than P, then take the A matrix you already have and take certain aij's that are 1, mark them out, and replace them with zeros.
Those that maximize.
So, okay, so which ones?
Those that correspond to
If this one, well, this still outputs QR here. If QR happens to be less than P, replace an aij, which is equal to 1, by aij equals 0 if something between I and j. some kind of an equality. If distance between Vi and Yj is equal to R. Yes. If the particular R happens to be realized by this coverage, in other words, Vi is being covered by Yj, there's a facility at the jth location, and he says that now I'm going to disallow or not allow this to be covered by Vi to be, I'm going to restrict the coverage of Vi to something other than Yj's, okay? Yj will not be permitted anymore, in which case you're simply requiring the coverage distance between Vi and whatever is going to cover that to be less than R. So you make that 0. He does these things without mentioning anything about the search over R. Well, he's, again, I think that's a very intelligent approach, because once you do this, things that used to be covered with an R will no longer be covered. Within exactly R will no longer be covered. So they will have to be covered by something less. And of course, you solve the problem one more time. In that case, you either get something less than or equal to or greater than P. So what do you do in which case? For example, if the new covering problem with the new matrix outputs a solution which gives you more than P, what do you conclude? Yes, the previous solution is optimal, because as soon as you eliminate the exact coverage distances, you're no longer able to do the same job with P or less points. Okay, so the previous solution is optimal. If you happen to come up with P points, it's still optimal. If you have less than P, you repeat. Yeah, you keep going like that. And this is certainly a finite search, because the initial A matrix, the ones are being replaced by zeros. Eventually, it will become either all zeros or you will stop somewhere, right? Because the stopping criterion is quite well stated. Okay, yeah.
Claim that if you find a solution with P centers, we claim that it's the optimal solution. But in fact, with a smaller R value, we can still find a solution with P, I think. Am I?
P or less. That's a possibility. When you reduce it, you may still obtain a solution with less than P or equal to P.
In that case, isn't that solution
Optimal?
better than the...
It is yes, it's surely better because the R value is reduced. Nevertheless, we don't know yet if that's the optimal R value for the P-center solution.
So if we find a minimizing solution as P-centers, that does not exactly means that it's the optimal solution. We can find P or less facilities with smaller R's. So we don't stop.
Okay, we don't stop at that moment. If we find P centers as the solution of the final, the last R cover problem, we reduce one more time, solve. If the output is more than P, then we conclude that the foregoing one is optimal. Okay?
We continue until we find an R value which results in a solution with P greater.
Exactly.
Greater than P.
Yes. As soon as you get something greater than P, you know that the one just before that is actually optimal. The one before that could have P or could have also less than P. If it has less than P, all you have to do is you append to it arbitrary number of missing centers to complete it to a P center if you wish. Okay? Does that make sense? Too long to write them down on the board, but you've got them all in your heads, I guess. Okay. Any other comments on this? Now, yes.
Do we increase R as integer, as an integer value? R as long
In Minieka's method, he doesn't even deal with R. He simply deals with the A matrix. But the way I came to this point, we actually are performing a search over a finite list of numbers, ordered list of numbers, the betas. And so in my search, I just pick a middle value for the most recent list, solve the set cover problem with the appropriate A matrix defined relative to that. And then depending on the result, I just truncate either one or the other half, and then continue until finally your list will contain exactly one number. Okay? So you stop at that point. Actually, it may contain more than one number, but all of those numbers would give you the same solution. That's also a possibility. In that case, you choose the smallest one. Okay? Okay. Have you solved set covering before? There are certain quick ways of solving set covering problems. If those conditions work, I'm going to give them to you maybe in the after the break. Let's take a 10-minute break now. Okay?